All right, Chemistry 3202, course overview, review. Moving on to a new section now, still in Unit 2. So Unit 2, Section 3, Lesson 1, Indicators. All right, this is dealt with on page 599 of your textbook, and there's a question in your textbook on this as well. And remember in the last section we did the STSE and we talked about how hydrangeas could change their color depending on what pH their soil was. It was dependent on their soil pH. Well, we're going to look at some of these chemicals now, and these guys are indicators. And these chemicals can actually change color depending on what their environment is, whether it's acidic or basic, and depending on different levels of acidity and alkalinity. So let's have a look at these. Here are the outcomes for this section, for this lesson. Okay, so by definition now, an indicator is a simple weak acid or a simple weak base which changes color in response to a specific change in pH. So it's a chemical here now that itself is a weak acid or weak base. So it's able to be ionized or it's able to attract the hydrogen. All right, so it's a weak acid or weak base, depending on the levels of the acid or base of the environment that it's placed in. So here's an example, I guess. It says a pH range in which an indicator molecule can change color from its weak acid form to the conjugate base form is a function of how strong the weak acid is. So if it's a stronger weak acid, then it's going to release its hydrogen at a much lower pH. If it's a weaker acid, then it's going to be reluctant to give away its hydrogen, and therefore it's going to release it at a much higher pH. So depending on where that level is, the indicator itself is one color when it has the hydrogen associated with it, and it's going to be another color when the hydrogen has been released. All right, so that's what's going on here. And in this case, we have an example of an indicator when we talked about the operational definitions of acids and bases. We referred to litmus. Litmus is one of these chemicals that's an indicator. It has two forms. In the acid form, when it has hydrogen associated with it, it's pink or red in color. Okay? And these are under low pH conditions. So remember, acids turn blue litmus red. So when litmus is red, the conditions are acidic. If the conditions are changed to basic, it releases its hydrogen, and now the base form of the litmus indicator is now Lt minus, which means it's lost its hydrogen. And now in this form, it has a different color. It's going to have a purple or blue color, and that's why we say bases turn red litmus blue. So let's have a look and see how this works. So two forms of the indicator, and there we go. So it's basically an acid, weak acid with its conjugate base, and here's the weak acid in the red form, and the conjugate base is in the blue form. And we can see how this is in equilibrium with water. We're reacting it with water and we're producing H3O+ here. So as this hydrogen is released, of course, we can see the conjugate acid-base pairs taking over, and there we go. So if we look at this guy, we can see that in the acid form it's pink, and in the base form it's blue. So how is this going to work? Well, how do we know that acids turn blue litmus red? Well, it's Le Chatelier's principle. Watch. If we put this in a container of strong acid, the H3O+ concentration is now going to be very, very high. Le Chatelier's principle kicks in and says, okay, we just put this in an acid. We need the equilibrium to shift back this way. In acids, it turns blue litmus red. Blue litmus gets pushed to the red side in the acid environment. So acids turn blue litmus red. If we look at the base side of this, I'm just going to cover this up now. If we looked at the base side of this, we can say, all right, what if we were under acidic conditions and we added this to a base? Okay, if we put OH- in this container, it's going to react with the H3O+ to make water, thereby dropping the H3O+ concentration, and Le Chatelier's principle kicks in again and says, hey, the H3O+ has now dropped. We need to get that back to normal. So it's going to shift in this direction. Bases, remember, bases turn red litmus blue. So it's shifting the equilibrium that way because of this stress. Under this high basic condition, it's getting rid of the H0 plus. So all of this acid is going to be pulled to this side to make it blue. So bases turn red litmus blue, acids turn blue litmus red. There we go, and that's how indicators work. And it just so happens that the two forms of this indicator have two distinct colors, and that's pretty powerful stuff. We can start using this. Another indicator that we like to use for our titration experiments in this section is an indicator called phenolphthalein. That's a mouthful. Looks pretty complicated to say, but it's phenolphthalein. All right, and this guy has a color change at about pH 8.2. Okay, below 8.2, the indicator is going to be colorless. It's not going to have any color, but as soon as we hit pH 8.2, it begins to start shifting from colorless to very, very light shades of pink until we get to pH 10 or higher, and the phenolphthalein turns to a deep red color. All right, and here's how this indicator is working. So we're seeing something like this. All right, here's the indicator. So we can see that in this form, the indicator is a colorless solution, so this is going to be below 8.2. And in this form, we know it's going to be somewhere up around above 8.2, 8.29, 10. Depending how dark this color gets, the darker this is, the more we're above 10. All right, so this indicator increases in intensity. So here's the equilibrium of this. We've got the acid form of the indicator, HPH. So pH is simply referring to the complex structure that phenolphthalein is. We don't really care about the chemical makeup of phenolphthalein. All we're interested in is the fact that it has an acidic hydrogen here, and when it's in this acidic form, it has no color. But as soon as it picks up a hydrogen, as soon as it releases that hydrogen and goes to the base form, see how that hydrogen is released? So we got phenolphthalein negative, which means now it's in the conjugate base form, and that takes on the deep pink color. And the pH range for this, of course, anything below 8.2, and the equilibrium pushes this way, and anything above 8.2, and the indicator would shift in this direction. All right, so there we go. Here's an indicator table, I guess, showing you the different types of indicators that we can use. Here's phenolphthalein down here, and you can see that anything below about 8.2-ish, all right, if I could just draw a line down here, around 8.2-ish. All right, we can see that phenolphthalein is colorless on this side in the acidic range, below 8.2. But as soon as we hit 8.2, you see it starts to get more and more intense, and it gets darker as we get to pH 10. Now what's happening here is this is the degree of equilibrium. As we start getting more and more basic, the equilibrium is favoring the product side, but it doesn't go with one foul swoop kabang, you know, you're on one side and your other. It starts to favor it, so it starts to push here. So this business right here, where it changes from light pink to really dark pink, is where we'll be starting to see the adjustment period. And as the pH begins to increase, it's shifting further and further and further to the product side. So if we go back and look at this guy, we can say that it's colorless to pink, but it depends on how far it's being pushed to this side. At pH 8.2, where it just starts to change color, this is where the acid form begins to lose its hydrogen, and we're getting a little tiny bit of the base form. So that's why we see a little tiny bit of pink. And as we get a higher pH, as we go from 8.2 to 8.5 to 9, the equilibrium is pushing further and further and further this way, so we're making more of this form. And the more of this form that's present, the more pink color that's going to be reflected, and that's why we see the darker pink. And as we get to pH 10, of course, this equilibrium now is favoring way, way, way to the side, so we get lots of this form, and that's why it gets dark. So for most of these indicators, we're seeing a gradual change in their color. It doesn't go swoosh. It's a gradual blending or change here as the equilibrium starts getting pushed further and further to the side. It gets darker and darker and darker. Same thing's true for all of these guys. You see a range. In this case, the alizarin yellow goes from a yellow to a series of oranges and pinks until eventually it gets to this dark color. Because what you're seeing here is a blending of the yellow form and a blending of the red form. So you're getting these oranges and pinks. All right, same thing up here. You're going from yellow to green to cyan to purples. And what you're seeing is a different level or concentration of each form that's mixing. All right, so on one side, one extreme, you get all the acid form showing the pink color, and as you start going to the other form, you start getting a different color. Now you might be looking at this guy and say, hey, this guy has three different colors. Well, this guy is special. Thymol blue has actually 3 colors associated with it, so it would be what's called a diprotic indicator. And if TH is representing the indicator, you're going to get something like H2TE, where this guy could produce the first one, which is going to be HTE minus and H3O plus. And then you're going to go a second time where HTE minus is going to release another hydrogen. Oh, sorry, then we're going to get just TE2 minus. TE2 minus. So what we're seeing here is that this indicator, the thymol blue, actually has 3 different forms. It has this form, which is red in color. It has this form, which is the yellow in color. And then when that completely changes, we're getting the purple color over here. All right, so 3 different forms of the indicator. Depending on what pH we're at, that's what's going to control what color we see. So this guy is useful for showing pHs that are around 2.5 and say 8.2, 8.4, like that. All right, so let's go have a look at some of these questions and see what can come up here. This is a typical public exam type question. And it's saying phenol red is an indicator known as HPR. So PR is representing phenol red. So a very complicated chemical formula here. But we're only interested in the fact that it's acidic. In its acidic form, it's yellow in color. And in its basic form, it's going to be red in color. So it says write a net ionic equation to show the reaction between phenol red and water. All right, so what we're going to do is simply the Bronsted-Lowry equation for that weak acid. And we're saying HPR is in the acid form, it's yellow, it reacts with water, releases its hydrogen to produce the basic form, which is PR minus, and that's going to be red, and the H3O plus. Okay, part B says, predict the position of the indicator equilibrium when a single drop of indicator is added to a container of nitric acid. So this question is saying, hey, we're going to drop this now in a great big container of nitric acid, H3O+. Well, we know what's going to happen, don't we? That concentration is drove through the roof. Le Chatelier's principle says we got to get rid of it, so it should shift in that direction. It should turn yellow. All right, so here's a little explanation of what's going on there. Okay, so the nitric acid is a strong acid. It's going to represent a very acidic environment. High levels of H3O+ is going to cause the system to shift to the left and therefore turn yellow. Part C of this question says, well, suggest a way now to shift the position back to the red color, because after all, this is equilibrium, and this is going to be a back and forth. Right now, we've caused the equilibrium to favor the reactants. But what we want to do is somehow shift this to now favor the products again. And of course, you guessed it, if this acid caused the reaction to shift in that direction, then what we need to do is neutralize all of this acid plus a little bit more to get the equilibrium to pull to this side to try and produce the red color. So what we need to do is we need to shift this to the right-hand side, and we need this to rise in pH. We need this to be basic. We need it in a basic environment. So what we need to do is neutralize all of the nitric acid plus a little bit more to make it a basic environment. So we want to get rid of all the nitric acid, neutralize that first by adding something like sodium hydroxide, and then add a few more drops of sodium hydroxide to make the environment. Now, we neutralized it, and a few extra drops makes it basic, which is now going to pull this indicator to the right-hand side and change it to the red color. Okay, here's an acid-base indicator table that you guys would have at your disposal. And this is given to you. This is at the department website under the chemistry link. It's also on the Desire to Learn homepage there. So you can get this printed off, but you will be given one of these on your public exam. And this tells you the name of the indicator and the ranges. Here's thymol blue. Remember we just talked about that having 2 possible color changes. So this is showing us the lower level and the upper level, and the fact that at pH around 0, this guy's going to be yellow, and at pH 1.6 it's going to start to change blue. So in between 0 and 1.6 we're going to get a gradient from yellow to blue. Okay, here's the indicator thymo blue. It's got two different pH ranges and it's telling you each one of these. If we look at phenolphthalein again, 8.2 to 10. So we said anything 8.2 or less is going to be colorless. As we go from 8.2, it's going to start changing to the pink color, and at pH 10 it's going to be really, really, really pink. Now that's going in that direction. Suppose we turned it around and said let's put it in a basic direction and then start neutralizing. So if we put phenolphthalein in a strong base, it's going to be dark, dark pink first. And then as we start neutralizing it with acid, it's going to start falling off this way. So it's going to get lighter and lighter and lighter and lighter until it hits pH 8.2, and then it's going to turn colorless. So again, depending on what direction you're neutralizing it, you have to watch what color it's going to be. All right. So if you're going from acidic to basic, it's going to go from 8.2 to 10, colorless to pink. If we're going basic to acidic, then it's going to start pink and fade off until it goes colorless. So a lot of information in this indicator chart. Okay, here's another type of public exam question from an old exam. It says, what's the approximate pH range if a solution is caused methyl red indicator to turn yellow and phenol red to turn yellow as well? So let's have a look at this. We're looking at this and we're saying methyl red indicator. So I'm looking at my chart. Methyl red is in the yellow form, which means it must be up around 6.0. And it also said phenol red right here is in the yellow form, which means now that's this range. So what we're saying is that it must be within the pH range of 6 to 6.6. Because if it was less than 6, then this indicator would be red. If it was greater than 6.6, then this indicator would start to turn red as well. But we're not. We're seeing yellow here. So in this particular example, we have to qualify it by writing out an answer, and we're saying methyl red changes color from 4.8 to 6. It's yellow, so therefore we're at pH 6 or greater. The pH could be 7, could be 8. It's still going to be yellow, right? So anything above 6 is yellow. And we look at this and we say, okay, phenol red, it changes color from 6.6 to 8. Anything below 6.6, it's yellow. Could be pH 4, could be pH 2. It's going to be yellow. But when we work these two together, we know we're not less than 6. We know we're not greater than 6.6. So therefore, we can give an approximate range as to where this unknown solution is. So it must be between 6 and 6.6. And that's how indicators are used to give you a range in pH. All right? You have an unknown solution, and by using two different indicators, you can get an idea of where the pH is between. Okay, there we go. Okay, here's another multiple choice from a public exam. It says a solution was tested with 3 indicators to give the results shown. What's the approximate pH? Well, what you have to do here, of course, is what we just did here. We have to look at this and say, okay, this guy changes, this guy will be blue under pH 5.4. Anything greater than 5.4 in bromocresol green is going to be blue. We're looking at indigo carmine from the table, and anything below 11.4 is blue. And then we look at thymolphthalein and anything above 10.6, and we know it's going to be blue. So what we've done is we simply isolated this and say, hey, it has to be between 10.6 and 11.4. So the answer to that would be C. We know it's not 9, because if it was 9, then these guys would be a different color. All right, so check your table on that. Here's another problem. This is a long answer question. You can see that this guy's worth 4%, so this is going to bring in a few different ideas. It says the following tests were performed on 4.1 mole per liter unknown solutions. Explain how you can determine which of these solutions is ammonia and which is sodium hydroxide. Now, what you have to keep in mind is we know that sodium hydroxide is a base, and we know that ammonia is a base. One of these is a strong base and the other one's a weak base. Now we know that sodium hydroxide is going to be 100% dissociated. So this guy is going to be a strong base. It's going to be 100% dissociated because it's an ionic compound, so we're getting a 1-to-1 ratio of the sodium to hydroxide solution. So in terms of the amount of ions that are being produced, this guy is going to produce 100% ions. So it's going to be a very good electrolyte, because remember, if it can conduct electricity, it's because it's got free ions floating around. And this guy's going to have a lot of free ions because it's 100% dissociated. So we know that the sodium hydroxide must be A or B. All right. We can also look at the ammonia and we say, well, that's a weak base. So what's going to happen with ammonia is that it's only going to be slightly ionized here. And therefore, we're not going to get a lot of ions. We're not going to get 100% ions like we did up here. So very few ions means we're only going to have poor electrical conductivity. So if we can look at our table up here, A or B must be NaOH, and C or D must be NH3 based on the electrical conductivity. Now what we need to do is we need to look at the pH. Because if sodium hydroxide is a strong base, then it's going to have a very high pH. It's going to have a pH up around, say, 10 or so, very, very high, 10, 11, 12, like that, because it's a very 100% dissociated. You get lots of OH minus. So if we look at our table and say, okay, phenolphthalein, we look at that and we're saying, what are we saying here? It's going to be blue above 10.6 and colorless at 9.4. So we're saying that this is a strong base, so its pH is going to be above 10, so it's going to be 10, 11, 12 like that. So chances are that this is where this guy is going to be, because this is going to be, what do we say, 10.6 here, and this is going to be 9.4. So chances are the sodium hydroxide is going to have a pH above 12 or thereabouts, and it's going to have a very high pH. And you can actually calculate the pH if you want, because you know the concentration is 0.1. So that's going to give me a pH of a pOH of 13. You want to calculate that? pOH is minus log of the OH minus concentration. So in this case, it's going to be the minus log of 0.1. So that's going to be a pOH of 1, which means the pH is 13. For the ammonia, it's going to be a weak base, so the level of this is going to depend on the percent ionization or the percent reaction here, which we know is way, way less than 100%. So therefore, the amount of hydroxide is only going to be very slight, which means the pH, depending on the concentration, is going to be much less than 10. And therefore, it's going to be this guy right here, C. Okay. Here's another public exam question based on indicators and calculations this time. It says a 0.1 mole per liter solution of weak acid caused litmus to turn red and methyl orange to turn yellow. We need to calculate the approximate percent reaction for this acid. So what we need to do is we need to find out, well, what's the pH of that acid based on the indicator information. And the indicator information tells us that litmus is red, and it can only be red at pH below 4.5. It's also telling us that methyl orange is yellow, and it can only be yellow above 4.4. So we've established our range, and we're saying that the pH here must be no less than 4.4, but it can't be 4.5, because if it was, then methyl orange would change color. So the pH has to be 4.4 based on the indicator information. Now that we have the indicator information and the pH, we can say that, all right, we can calculate H3O+. It's going to be 10 to the minus pH, 10 to the minus 4.4. We get the hydronium ion concentration, 3.98 times 10 to the minus 5. And now we can find the percent ionization because we know the initial. And the percent ionization is based on this formula right here. Percent reaction is H3O+ divided by HA initial times 100%. And we put our values in, 3.98 times 10 to the minus 5 divided by 0.1, and we get 0.040% reaction. So that's a nice little question. That's one of those level 3 questions where you have to put a whole bunch of stuff together. You have to know about indicators. You have to know how to do this calculation. You have to know about percent reaction. You know it's a weak acid, so you know it's not going to be 100% ionized. There you go. Okay. Don't forget now, our online tutors available. Check their schedule. Don't forget the online material. We've got tons of stuff there. Check it out. And if you have any questions on this, don't hesitate to drop a line in the discussion box there and let someone know that you need a question answered, and we'll try and get to you. All right, see ya.